Hi, everyone. Welcome to Anritsu's Lunch and Learn webinar. Today, we kick off a new VNA series with a presentation on VNA's Fundamentals Part 1, Architecture and Measurements. This will be presented by Arno Patai, Field Applications Engineer with Anritsu. Before we get started, I wanted to go over a few items to help you participate in today's event. You have joined the presentation by listening to your computer's speaker system by default. If you would prefer to join over the telephone, just select phone in the audio pane and the dial-in information will be displayed. Anytime during the presentation, you have the opportunity to submit text questions to the presenter by typing your question into the questions pane on the control panel. We will collect these questions and address them during the Q&A session at the end of today's presentation. Today's webinar is being recorded and you will receive an email within the next few days with a link to view the recording. I would now like to introduce Arno Patai.
Thank you, Tina. Good morning, good afternoon, good evening, everyone. I hope you're all keeping safe and sound at home and staying healthy. My name is Arno Patai, and I'm a field application engineer here at Anritsu. I've been with the company almost 20 years, and I've been in product marketing, field sales, and now field applications engineering. So I have 35 years total in the industry, RF microwave. So I welcome you all to this two-part webinar entitled Vector Network Analyzer, or VNA Fundamentals. So this first part, we will be talking about architecture of the instrument and measurements. And then we'll have a second part, which will be on air exactly 1 week from today. As many of you know, the VNA is really one of the most important instruments on an RF or microwave engineer's test bench. I like to think of it as the Cadillac of the bench. You may have other instruments revolving around it, but the VNA serves as really the key test and measurement instrument. So let's go through what we're going to cover in the next two sessions. Today we're going to, as I mentioned, look at why users need VNAs. What's the purpose of the VNA in the first place? Some of the basic terminology and the measurements involved. So today we'll primarily talk about what we call SParameters, which are measurements of transmission and reflection characteristics of the devices we're going to be testing with this instrument. We'll look at, in quite some detail, we'll look at system architecture and really capture what are some of the key components within the instrument. In the second part, we'll dive into the calibration methods, because it's very important to understand that a VNA, unlike other instruments like spectrum analyzers and power meters that come with instrument calibrations from a cal lab, VNAs require user calibration. So we'll talk at length about what are the calibration methods and how those, together with the VNA's base specifications, contribute to the accuracy and uncertainty of the measurements that we're going to make with the instrument. So this is very important to really understand how the VNA, first of all, how it works, how it makes the measurements, but then how it applies the error correction that's vital to getting accurate measurements. And then at the end of the session next week, we'll talk about advanced measurements as well that are beyond the S parameters. So let's start off with why users need VNAs. The VNA is really best thought of as a stimulus response instrument. In other words, it generates its own test signal, and then it applies it to the device, and then it measures various signals that are coming back from the device, both signals that are transmitted through the device as well as reflected from either interface of the device. So we're looking typically at transmission reflection characteristics, and we'll talk in a moment about how we capture those measurements and then translate that into S parameters. VNAs are used in multiple environments. We characterize devices in R&D, in engineering. We test devices and subsystems in manufacturing. And we also have needs for VNAs in the field to test at cell sites and other remote installations. VNAs are used with different packages and configurations. So this is where the challenges lie when we're trying to perform things like user calibration. How do we interface with the VNA? Do we need some fixturing? Do we need a probe station? There are other various methods that are used to transfer the reference plane of our measurement to where we want it, so that we're measuring just the device and nothing else that's connecting to the device. So we have to consider these different packages and configurations when we perform the user calibration that we'll cover next week. But we have most commonly coax devices. We have 2-port, we have multi-port, we have differential inputs, single-ended, we have waveguide devices, we have devices that I mentioned are in fixtures. So that presents its own set of challenges. Probe stations, we're looking at semiconductor wafers. And then we have another class of very interesting measurements called optoelectronic, where we're looking at E to O and O to E, which are cross-domain measurements. So we're measuring optical modulators and receivers and transceivers, and we're using an electrical VNA to do that. That'll be a subject of a whole nother webinar in the future. But the basic measurements, again, S parameters, forward and reverse transmission, forward reflection, reverse reflection. So those are your basic 4 S parameters for the 2-port case. But today's modern VNAs do a lot more than just that. They also, in addition to sweeping frequency, they can also sweep power. They can also offset tune to other frequencies. So we can look at other measurements that were typically done with other instruments, power meters, for example, for gain compression, spectrum analyzers used to do IMD and harmonics. So we have a lot of flexibility in today's VNA hardware to do a lot more than what we were able to do in the past. And then beyond that, there's composite receivers that can be added to do noise figure. We also have the inverse FFT algorithm to convert frequency domain information to time domain, allows us to spot where we have impedance discontinuities on a line at specific locations. And even with transmission measurements, we can now look at eye diagram simulations based on S parameter transmission data. So to kind of summarize here, there are a lot of different devices. They're in different classes. We have active devices such as amplifier switches. We have filters, adapters, circulators that are considered passive devices. Cables, connectors, and backplanes, that's part of the high-speed interconnect components that we also look at with the VNA. And then we have more of the subsystem type of application. Okay, now we're going to go through some basic terminology. We talk about the VNA as a vector network analyzer. In the past, there were scalar network analyzers as well. Okay, we have to talk about the difference between passive and active devices, and then transmission reflection measurements, which then form the SParameter matrix. So first, vector versus scalar. Well, RF signals have not only magnitude, they have phase associated with them too. So vector captures that information, magnitude and phase of the signal. A scalar is just magnitude only. So it's pretty easy to conclude a VNA measures both magnitude and phase. A scalar only has magnitude information, and in the past, they were quite limited in dynamic range. So over time, VNAs have pretty much replaced scalars and have become more affordable. And of course, they do a lot more. They make a lot more measurements than SNAs ever did before. Passive versus active devices. Passive devices consume energy, they don't produce energy. So we're talking about something that attenuates the signal going through. So we associate loss with that. So insertion loss will be the measurement that we look at in the transmission sense. For active devices, we apply a DC voltage, and we typically get amplification. If it's a good amplifier, we'll get amplification. And so we'll have gain associated with the transmission measurement. So that's a distinct difference between the two then. One has gain, because it has DC bias, the other does not and has loss. So we take all of the measurements here, transmission, we look at insertion, loss, and gain. So basically that's going to be the signal decreasing from input to output, or in the case of gain, increasing from input to output. And we're looking at the ratio. So at all times, we're capturing the signal that we're applying to the device, and then we're making measurements at both the input interface where signal is reflected back and the output where signal is transmitted through. So we're doing those ratios against what we applied to it. Because remember, this is a stimulus response instrument. And in terms of return loss, we're measuring what's being reflected at either interface. And then again, it's the ratio of what we measure reflected against what we sent in the first place from the source side. And then once we have all the transmission reflection characteristics for our two-port device captured, we can then assemble them into what's called the SParameter Matrix. And here the nomenclature is very simple. The second number in the subscript is where we're applying the signal, and the first number is where we're measuring it. So at all times we're applying a signal, and then we're measuring it either on the input side or the output side, depending on what we want to look at, and then make the various ratios. And then once we have all the S parameters collected, we can present it in a standard format, such as the S2P format. And that's what's typically used in simulation, circuit simulation. So it's a very useful notation that's used for capturing S parameter information. This is our typical setup. In a two-port case, we have a benchtop VNA here with two ports, port 1 and port 2. We have test cables attached. And we have a device, very simple device in this case, passive device, and we're measuring transmission. So you see the green arrow going across from port 1 to port 2. Then we also have a green arrow reflecting back at port 1. There would be a similar one at port 2 as well. And in so doing, we're able to measure all of those signals, both the ones transmitted forward and reverse, as well as the reflected forward and reverse. And at all times, we know what we're applying. So in the denominator of our ratio measurement will always be what we apply, and in the numerator will be what we measure, either in reflected or transmitted sense. So to kind of collect the different transmission measurements that we've talked about thus far, we mentioned gain, insertion loss, those are very common. And those are scalar quantities, so there's really no phase associated, but then there's also phase that can be measured because we have the VNA. And then the full transmission coefficients are the full complex representation of the transmission that carries both the magnitude and phase information. And we can separate that to real and imaginary if we want to just stay strictly in complex terms. And we can look at electrical length, both in terms of distance, in terms of time. And then we can look at, in a transmission sense, how much is our phase deviating from linear. That gives us an indication of how good our linearity is, and also tells us a little bit about the group delay of the device. And we'll talk about that in a moment. On the reflection side, we have return loss. That's the most common, again, a scalar measurement. And then we have the full reflection coefficients, which are the complex quantities, S11, S22. We can look at these in terms of time. This is where we do the inverse FFT and get the time domain information. And we can look at things on different charts, such as a Smith chart, to determine what the actual impedance is, both the real part and the imaginary part. And that tells us a lot of information about how well our circuit is matched to, say, a 50 ohm ideal case. SWR is similar to return loss, is also scalar quantity, but it's another way of looking at reflection. So the front panel basic view, when you turn on a VNA and preset it, a two-port, is to present the S parameters in the following way: S11 in the upper left, S12 in the upper right, and then the lower left is S21 and lower right is S22. So this is typically how it will look when you preset. Of course, you can change things later to use different displays, but this is the basic presentation of the S parameter measurements. So it captures all of the transmission and reflection characteristics of the device. So this is kind of a copy of what you just saw in the previous slide, but this is showing what we're really looking at on each particular graph. So in the Smith chart, we're going to look at reflection coefficient. So this is a complex quantity. So this is going to tell us not only the resistive part, but also give us the reactive part. So it's going to tell us whether something is inductive or capacitive. Same is true for the S22 on the lower right side. And then the other two graphs are showing the transmission, both magnitude and phase. So S21 is the forward direction, S12 is the reverse direction. And then if we just take the scalar portion of that and omit the phase, then we just break down into the return loss for the reflection, S11 and S22, and just insertion loss, or if it was an amplifier, it'd be gain for the S21 and the S12. On the Smith chart, you'll notice that there are circles that represent constant resistance. So you can see we're in the center, we're intersecting right at 50 ohms. So that's where we want to be when we make a measurement. Typically, that's not going to be the case. And so we'll quickly be able to determine if something has an inductive part to it or a capacitive part to it, because it'll either end up in the upper hemisphere, it'll be inductive, lower hemisphere will be capacitive. And if you have a full short, it'll end up over on the left side. If you have a full open, it'll end up on the right side. So there's a position here for every single impedance in a complex sense. So that's used more for reflection measurements. But for transmission measurements, oftentimes when we're looking at amplifiers, it might be useful to look at a polar display where the distance from the center is the magnitude and the rotation around the circle is the phase. And then I mentioned group delay. Group delay is specifically the rate of phase change with respect to frequency. So if you have a nice linear phase device, then phase will change as a function of frequency. It'll be a straight line. And therefore, when you take the slope of that, you'll get a constant group delay. And that's what you want to see when you're designing a filter, for example, because if you've got wideband signals that you're trying to filter through the device, you don't want to have non-uniform group delay, because that'll create distortion in those wideband signals. So it's important to make sure that the phase change is linear with respect to frequency in that case. So you can see with the filter that as you get to the edges of the filter, you really start to see some peaks show up there. And those are the areas really to be avoided, and you want to get the signal more or less in that central section where the group delay is flat. Okay, so now we've covered the basic measurements, and we'll come back in a moment to those. And we're going to now look at the hardware that's really behind the VNA, what's inside the VNA, and how these measurements are made. So as I mentioned from the very beginning, we're dealing with an instrument that has a source. So it's a source response, stimulus response system. And so we have a full synthesized signal generator in the source. And we then have a test set, which includes the components that allow us to separate the transmission and reflection signals that we're interested in measuring with our receivers. So that's part of the microwave test set. And then behind all of that, we have the analyzer itself, which is really the digital analog hardware, the IF sections where we have the A to D and the amplification at IF, and then the firmware and the software, of course, the front panel display and memory as well. So that's what makes up the building blocks of the VNA. Now, if we just focus on the source and the test set part of the block diagram, so basically the RF and microwave sections, we have the source at the top. We have a transfer switch that regulates which direction the signal is applied to the device under test. And then you'll see we have reflectometers that allow us to separate signals coming back from either interface from signals going through the device in either direction. And then we have 4 receivers in the center, 2 of which are going to be known as reference receivers because they capture the signal early on, and that goes in the denominator of our ratioed measurement. The B1 and B2 receivers are used to capture what either gets reflected back or gets transmitted across. So the B1 and B2 will typically end up in the numerator of our ratioed measurements, and A1, A2 will end up in the denominator. So if we're going to go look at S11, we're going to apply a signal. We're going to sample it at A1 on the forward side, and then we're going to measure the signal coming back B1, and that will be the reflected signal from the port 1 interface. So we'll take B1 over A1 to get S11. And then on the transmission side, S21, again, the reference is still A1 because that's the direction we're applying the stimulus. The ratio then ends up being B2 divided by A1, and that will be S21, which is our forward transmission. So that's how it works in the forward direction. And analogously, on the reverse direction, it's the exact opposite. The switch goes over to the right-hand position. Signal is applied from right to left in this case. And again, it's tapped at A2 as the reference, and then measured at B1 for transmission and B2 for reflection in the reverse case. Okay, so next we're going to talk about the key components that were in the block diagram that you just saw. First and foremost, receivers. That's an extremely important part of the VNA. It sets a lot of the specifications for the instrument, such as noise floor, also IP3 or input compression. Mixers are typically used at low frequencies. They work really well down there. It's what you'll see in most RF VNAs. So when I say RF VNA, I'm referring to VNAs that are typically below 8 to 10 gigahertz. And then microwave VNAs would be going higher in frequency, of course, to gigahertz and beyond. And at those frequencies, we would want to use something that is a little more flat in terms of its conversion loss. So we elect to use samplers, oftentimes at higher frequencies, to get better noise floor and more constant conversion loss. Because mixers tend to roll off at high frequencies, and then you end up using harmonic mixers just to be able to get to higher frequencies, and that can translate to quite a bit of loss in terms of dynamic range of the instrument. So receivers are very important. We're using higher LO frequencies now so that we can get better dynamic range, lower noise floor. We have higher IP3, so better linearity in a lot of these receivers today. And we can extend these to higher frequencies unlike ever before. So we can push these kinds of sampler structures to as high as 220 gigahertz, potentially even beyond. So again, the key benefits of the sampler technology: the flat conversion loss, the low noise floor, the higher IP3 or higher compression points versus the mixer. But mixers work very well at low frequencies. Samplers typically roll off, don't work down there. So there's a place for both. Same with reflectometers. There's two distinct ways of doing this. You have directional couplers, which are typically used at high frequencies in microwave VNAs, but they are wavelength dependent. So as you get down to lower frequencies, they will roll off because of the fact that they have wavelength dependence. So they don't work too well at low frequencies, but directional bridges, which are used more in RF VNAs, do work well down there. So in the ideal case, you would want to be able to combine the two together, just like in the case of receivers. For reflectometers, you'd like to be able to use both so that you can create the most broadband VNA possible. Same with switches. Switches too have distinct technologies and therefore advantages at various frequency ranges. So we use FETs typically at low frequencies, pin diodes, switches at higher frequencies, just to be able to optimize things like insertion loss, isolation, as well as compression. Again, the IP3 or IMD performance of the switch. And then finally, the source. That's also very important because the source is going to determine how your high-level noise looks, because it's related directly to the phase noise of the source. So we want to have a fairly clean source. It doesn't have to be perfect because we're doing ratioed measurements, so a lot of the phase noise gets canceled out when we're doing ratioed measurements. But we do want to make sure that They are locally synthesized. We don't need to lock it through an IF or anything like that. We need to be able to have independently synthesized, both in terms of the source as well as the LO that's used to drive the receiver and do the down conversion. So, but the main point here is phase noise and how it translates to high level noise. That is a key point, especially as you go higher in frequencies to the millimeter wave side. So just as a quick summary, what we've covered so far, VNA is an instrument that provides extremely accurate characterization of RF and microwave devices. So we can look at not only the lowest sort of component in the food chain, but all the way up to subsystems that are designed using the various components. We're providing a ratioed measurement relative to the incident signal. So basically we're capturing the incident signal that goes in our denominator, and then we're measuring either the reflection or the transmission and ratioing that against the incident signal. And we're providing both magnitude and phase information at all times. And with these receivers that we have in today's modern VNAs, we get very wide dynamic range and extremely linear performance. So that's also important when trying to maintain accuracy of your measurements. You don't want to overdrive your receiver, for example. The challenges that lie are we have a lot of different application environments, and this is where we really spend most of our time as VNA users, is trying to determine what interface we're going to do our calibration at, what cal kit we're going to use. So there's a lot of subtleties involved here, depending on the application, because as I mentioned at the beginning, the VNA without the user calibration is not very useful. You don't get the accuracy until you perform the calibration at the user level. And we'll talk about that in next week's session. So we have a lot of different calibration choices and some post-processing tools to allow us to optimize what we're trying to measure. And we'll review those next week in the session. And of course, we have a lot of information on our website that I welcome you to take a look at, both application notes and measurement guides. So now in the remaining few minutes, I'm just going to mention, before we go to questions, I'm going to mention our product portfolio and really everything we've talked about here today as far as the VNA architecture and the basic measurements applies to all of the different VNAs out there. Anritsu does have a very wide portfolio of VNAs, from the most basic, what we categorize as economy series that are mainly used to test passive devices, mainly 2-port, maybe a handheld like a VNA Master or Microwave Site Master. So there are different basic VNAs available at the economy level. And then we have some mid-performance VNAs that have some more power control, go to 4 ports, may go to millimeter wave banded coverage. Those are in the performance or mid-performance category. And then at the very top end, the high-end performance VNA is our Vector Start series. And that's the one that has the dual architecture that I've been alluding to, where we really make the best of all the technologies available to construct a very wideband VNA that's able to cover kilohertz all the way up to gigahertz frequencies. So we're using combinations of component technologies to do that. Next, I'm going to do a short demo. I have an instrument here, and I'm broadcasting to you today from Morgan Hill, and I have an instrument here at our division site, and I have it connected over the internet here, so using a Screen Connect software. So what I'll do is I'll bring that up. And the setup that you see there is fairly basic. I have a 110 gigahertz VNA, so, well, maybe not that basic after all if it's 110, which is a 70 gigahertz mainframe VNA plus a test set that then interfaces to some millimeter extender modules that are on the tabletop. And then that's connected to a PC board that has a trace on it. So what we're going to really measure here is that trace and look at the S parameters of that. A calibration has been done at this point using a a coax cal kit. In this case, since it's 110 gigahertz, a 1 millimeter coax cal kit. And the calibration has been done to the ends of those cables that are pictured here. So I'm going to switch over to my VNA screen. And what you'll see here is the user interface. And across the top, we have some very basic menus, file, channel, trace, and onward. And what's important as a user is just basically to follow the flow here. Set up your instrument with the appropriate frequency that you want to cover, the power level that you want to test at, because remember, there's a source in here, and we can adjust the power level just as well as the frequency range. We have different sweeping capabilities. We can sweep in frequency, we can sweep in power if we're looking at compression measurements. And then we have the averaging and IF bandwidth controls here as well. So these allow us to optimize our measurements and provide a little bit of noise reduction at the expense of increased sweep time, but sometimes we need to get that additional accuracy, and the IF bandwidth is really our way to adjust dynamic range or sensitivity versus sweep time. So it's important to set up the channel the way you want it before you proceed to do the actual user calibration, and that we'll cover next week in the session. On the trace side, this is where you select what you want to measure. So in a typical channel, which is an instrument state in this case, with a calibration applied, you could have up to 16 traces. And each of these traces could be then set to a particular response. So for example, you see trace 1 is highlighted here, and it's currently set to S11. You can see all the S-parameter choices are here. We can also do user-defined ratios where we maybe put a 1 in the denominator, and therefore we're measuring power as opposed to a ratio. We're measuring something that's unratioed. It'll be a power measurement. And we'll talk about those calibrations next week as well. Then beyond that, we've got display. So we can choose, as I was showing earlier in the presentation, we have a variety of different ways to display our data: log magnitude, phase, real and imaginary, SWR. We can look at impedance, we can look at the Smith chart, log mag and phase. We have group delay also down here at the very bottom of the list. And we even have the power. This would be for a non-ratio measurement. If you just want to look at output power, for example, and you're doing gain compression. And then we have scaling. So scaling is going to be appropriate to whatever display we're making active. So in this case, it's the Smith chart. If I make the S21 the active trace, then of course the scaling is appropriate to that measurement. And then finally, we have some markers that we can use, that we can set up on any of the traces, and basically look at what the measurement result is at a given frequency. So those are the basic controls. Channels, again, are best thought of as complete instrument states. This is what you want to make sure you set before you begin the calibration process. And then once you've done the calibration, or even before, you can set up what traces you want to measure. But the important thing is to get the channel defined first. And then, of course, it's always advisable to save your setup so that later you can recall it again. And so that's in the file menu. So, but basically, we're going to walk through from 1 to 8. We're going to go all the way across the menus. And we'll continue this next week with the calibration view, and we'll go through some of the details of calibration, both manual types and automatic calibrations, and even on wafer kinds of cases. So I'm going to switch back to the presentation. And at this point, I'm going to ask if there are any questions. Finished a little bit sooner than I had expected, but I think we got through everything reasonably well.
Great. Thank you so much, Arno. We're now going to begin answering the questions that came in. I do have a few of them. And everyone listening, you can still submit questions as we go through this last slide. And Arno, the first question, why does the DUT use different gender SMA connectors? And that's from Antonio Guillen.
Okay, Antonio. So it depends on the device itself and how it's been designed. Often what we find is devices have female connectors on both input and output. But there are some instances with filters where they're designed with a male on one end and a female on the other. And this becomes part of the challenge as a test engineer to properly characterize these devices, because you want to make sure that what you're measuring is purely the device and nothing else. So if I have to use adapters to adapt to something that has an opposite gender, I want to make sure that that adapter does not become part of my measurement. So so there are some techniques when we're doing calibration where we can either use insertable adapters that can be swapped out to change gender so that we can measure exactly what we want to measure. There may be cases where we have to de-embed something, and de-embedding just basically means that we remove it. So we have to basically characterize the adapter first and then remove it later so it doesn't become part of our measurement. The goal always is to measure only the device, and everything else connecting to it needs to get removed. So that's where the challenges lie with multiple genders on the devices.
Thank you. The next question is from Herbert Ariza. How does VNA replace a spectrum analyzer? And then I think it said for IDM.
IMD, yeah. Herbert, yes. What I meant to say there is that a spectrum, we can perform some of the same measurements with a VNA that would traditionally be done using a spectrum analyzer. I'm not necessarily going to say it replaces it, because there are some advantages still for the spectrum analyzer, given it has a lower noise floor, etc. But if you're looking at having one instrument to do everything, then a VNA can serve that purpose. So we can make measurements such as IMD by having a dual source in the VNA and creating that two-tone stimulus internally, or we could use an external source and combine them. And then the important thing, once we connect to our device under test and look at the output side, is we need to be able to offset tune our receiver to the proper frequency where we expect these IMD products to be. And that's something that modern VNAs can do very nicely now. We know where that signal is. We're measuring a known signal as opposed to an unknown signal. So this is where we can really excel with the VNA, because we can do some things like sweeping the tones and then looking at where the IMD products are as a function of frequency. That cannot be done very easily with a spectrum analyzer, because the spectrum analyzer just gives you that classical IMD view with the two tones and the products. So the vector network analyzer can, in that case, excel beyond a spectrum analyzer. But I think it is a little bit strong statement to make that it can totally replace it, because there's going to be things that a spectrum analyzer does very well and will always do well, and the spectrum analyzer has a place on the same test bench as the VNA and other RF and microwave instruments.
Thank you. The next question is from Al Guarino. Can you quickly review NF measurements, or will that be in a later date, specifically composite receiver?
Hey Al, how you doing? Yeah, I wasn't planning on covering noise figure in this session because this is more of a basics session, but noise figure again can be done with a spectrum analyzer. So there's another example of a case where spectrum analyzers can do the same measurement. Sometimes they excel doing that more than the VNA. But again, to do it with the VNA requires us to have a composite receiver, because we need to get our noise floor down as low as possible. So we need some preamplification to do that. So it becomes an additional accessory that has to get added on to the VNA to make noise figure measurements. And where the VNA excels again in this case is that we can do these things under swept conditions and actually look at noise figure as a function of frequency. But no, in this case, no. We'll look at possibly covering noise figure in a future webinar. But this is more about fundamentals today. Thanks for the question, Hal.
Okay. Arno, can you confirm that showing mixture measurement is also going to be in a future session?
Sorry, what was that? Mixer measurement?
Mixer measurement. Are we going to have that in a future session?
We'll look at that. I don't have a plan right now, but we can look at that. It will involve
Jay Johnson.
Okay, Jay. Yeah, we'll look at including that as another topic in the future because we can have a lot of different topics on VNAs. Certainly, given the versatility and flexibility of this instrument, there's lots of measurements that a VNA can make. But most importantly for the mixer measurement is going to be having, again, that ability to offset tune the receiver to where we expect the output signal to be in the case of a mixer. Just like in the case of IMD, we have to be able to independently move the receiver to a different frequency from the source because that's the way the mixer works. It's frequency translating.
Okay. Next question is from Francisco Romero. What is the best site for Anritsu VNA measurements examples?
I would say, Francisco, it would be our website. We do have a number of application notes there that describe different application scenarios with VNAs. That would be my best advice. We also have a document there called the Calibration and Measurement Guide that goes into a lot of detail about the various measurements we can make with the VNA. So I think the best resource would be our website under the VNA page.
Thank you. The next question is from Michael Ramsdale. In your real-time measurement, your DUT shows the phase rippling and not flat. Is this because the passive trace has reactive characteristics? What sort of passive device would have a linear phase plot?
Okay. Hi, Michael. Probably the best example for linear phase would be a cable, something that you insert or an adapter. I think the reason why you didn't see it in that live demo in the phase plot was because it's happening so quickly. It's reversing back and forth between 180 degrees back and forth because it's high frequency. So I would say it needs to be something a little bit shorter in terms of the wavelength to be able to actually see the linear phase. But yes, what you want to see is phase that is essentially a straight line. But as you know, if we go up to 180, we're going to flip back over to minus 180 and we're going to start over again. So it's kind of hard to spot that in the way that the display was set up.
Okay. Jay Johnson has another question. Can you show how to do a mixer measurement? Oh, in a future session? Okay.
We will consider that, yes.
Okay. And let's see. Okay, then Herbert, the last question I have is for Herbert Ariza. What SiteMaster cannot measure shot and open in Smith chart?
Why
some SiteMasters cannot measure shot and open in Smith chart?
Okay, so it depends if the SiteMaster has the ability to show the Smith chart. That's really going to be the display format that will allow you to see the complex impedance representation. If you're just looking at return loss in the normal SiteMaster mode, then you would not necessarily be able to see that. It has to be more in the VNA sense where we have the Smith chart display available. So it's probably the mode of the instrument that needs to be set to be able to view the Smith chart.
Okay, that is the last question I have, Arno. So again, I'll share these comments Thank you so much for them with Arno, and he'll review the questions if there was anything oversighted. So on behalf of Anritsu Company and our presenter, thank you all for joining us today, and have a great rest of your day.
Thank you all for joining. Stay safe out there.